Damiolini, who is going to talk about conformal blocks from vertex operator algebras, some geometric properties. And people online, please feel free to ask questions if you feel like. And of course, here also.
Okay, thank you. Everyone can hear me, right? It's okay. Yes, thank you for the invitation and the introduction. So I'm an algebraic geometer. So as such, I use vertex operator algebra to study some geometric objects like moduli spaces of curves or bundles over curves. And I want to, today I just want to tell you how we can construct some spaces of conformal blocks or vector sheaves of conformal blocks and which properties they have depending on, of course, the properties of the vertex algebras and representations they are attached to. So maybe to start, what are we going to see today? So the idea is that I want to study geometric properties, and I will say more explicitly later what I mean, of some sheaves. Let me call them V over mg bar. And by this space, I mean the moduli space of genus G and marked curves. What does it mean? This is just a geometric object whose point there, so if I take a point in here, this corresponds to a curve. You can always imagine it maybe to be a Riemann surface, if you prefer, with endpoints. And I allow my curve actually to be nodal, and I prefer to draw it as a curve and not a Riemann surface. So it could be something like this. And my n-mark points are smooth. Okay, so each point here is an object like this, a genus G curve with n-mark points. And I want to study a sheaf, which is defined over here. What does it mean? A sheaf is just to every point of mg and bar, I should give you, let's say, a vector space so that everything varies continuously. And I want to say that these sheaves depend on some representation theory. So the representation theory here are going to be given by a vertex algebra and some of n representations. Let's say simple, maybe. So, and the geometric property that I will investigate today or will discuss about it is, maybe there are two properties. One is actually, what is this sheaf? Is this locally free? So in general, sheaves can, as I said, just an assignment to each point, some vector spaces. This could be infinite dimensional, and it has to vary smoothly, but nice sheaves are locally free. I mean, locally, they really look like a vector space, and the way in which it's not globally just a vector space, it's given by linear transformation. So, and the other property is global generation. Meaning, can we describe this sheaf as just a quotient of something that it's actually trivial? It's really a vector space times the structure sheaf of mg and bar. So, and feel free to interrupt me for any questions, as Anne was saying before, like, just stop me. So before starting, I just want to say a couple of words on my assumptions on the vertex algebra and the modules at the moment. So I will just assume, I guess, my vertex algebra is positively graded, and what I will assume, of course, is that it's conformal. We have an action of the Virasoro, and I assume it's of CFT type. And I want to say maybe it's simple. It's not going to change much. Okay. And my V modules M, by V module, I really mean maybe admissible modules. And I want them to be simple. And I assume that, right, admissible meaning that there is a graded action of V on M. And so, and I will call A of M the conformal weight. Meaning L0 acts by the degree plus AM. I guess those are my assumptions. And I might add some extra later to make things easier, to show things. But for a second, just let's assume we only are in this situation. And so the goal is, the first step is, how can we even define sheaves, right? So how can we define objects? Or in this case, how can we assign, given maybe a curve with endpoints, right? So this is a point of MGN bar. And given a vertex algebra with n modules, so the question is, how can we cook up, let's say, a sheaf, a vector space. And of course, I can just say, well, there are many ways in which these assignments give us a vector space, but I want something that should satisfy nice properties, meaning the spaces here should be the dual concept of what conformal blocks are, or better, conformal blocks are the dual notion of what I have. So in particular, beside this property of being locally free underlies a more important property, which is a factorization. So maybe let me say that I want to cook up a vector space, and this should sort of satisfy factorization. And I'm going to explain what this means in a second. So maybe I first want to give an intuitive idea. So the idea is that on this space, right, MGN bar, I have curves which are smooth, the intuitive idea. So on MGN bar, maybe this curve here, this could be a curve with my endpoints, but maybe I have a curve which is nodal, or which has more nodes, or even maybe disconnected or something. And I would like to relate maybe a curve which is nodal, and if I can define here an appropriate, suppose this is a curve with the points. I would like to describe this in terms of something similar, which lives now, which lives now on the normalization. Right, so here I have a node, and I can take the normalization. What does this just mean? Maybe thinking backwards, if I start with this curve and I glue together Q1 and Q plus and Q minus, I get back this curve. And factorization tells me it's a formula to describe essentially this space, which is attached here over this curve, in terms of similar spaces. Let me call them V without the decoration. We have to figure out how to decorate them, which naturally lives over the normalization. And here I'm over now a smooth curve, or a curve of lower genus. And so using this process inductively, this property will essentially allow me to compute the dimension of these spaces. So this is sort of the spirit of factorization. And So that I want to mention here, because very often people will tell me, oh, just cook up some random vector sheaf, just take tensor product of the modules and you're done. And I'm like, yeah, but this doesn't depend on the curve. It's just a constant infinite dimensional sheaf. Thank you, but what do I do with them? So, you know, I didn't need to have a vertex algebra, right? I just need to have vector spaces to do that. So I want something more. And so how do I do this? Well, I start the work which I will present now is based on work with Angela Gibney and Nicola Tarasca. And it starts, maybe we heavily are influenced heavily by works of Frankel and Ben-Zvi, who define these sheaves on MGN, so only on smooth curves. And what we did was, well, we managed to extend the definition to the boundary, and so to finally have factorization. But maybe let's take a step back and see what they actually did, and so how to maybe get the definition for nodal curves, starting with the smooth curves. Although I will not give too many details, but I'm here until Friday, so we can talk a lot about this. Okay, so as I said, maybe I wrote there, let me just start with a curve and a point, just for simplicity, and I have vertex algebra and a module, and I would like to cook up something that I call, there are different, yeah, so let me call it in this way. This should be a space. So how do I do this? Well, before going into the maybe theory of Frankel and Ben-Zvi, I want to maybe take a step back from vertex algebra to Lie algebras, or better, when I consider the vertex algebra of defined vertex algebra, where L is a positive integer. So in this context, one can define, I mean, Tsuchiya and Yamada define what conformal blocks and study their properties quite easily. And the way in which we can do this is as follows. So we know that every module here is, and please forgive my notation, I'm not sure whether this is the standard one. Let me call it. So I take in a reducible representation of G of level at most L, and I know that every simple representation of the defined vertex algebra is given by the Verma module construction and induced up to representation of LLG. Right? This is nothing but let me just call it plus something like this. So, or maybe it's a quotient of that by the reducible, by the maximal ideal. So how do I construct a vector space starting with this data? Well, I take my space L of V lambda, and I notice that actually there is a Lie algebra acting here. Maybe it's better to put this arrow here since it acts on the left. And the Lie algebra acting is the following. Meaning I take the Lie algebra G, I extend the scalar with the coordinate ring of the curve minus the point that I had specified. And it turns out that by the way in which the Lie bracket works here in the residue theorem, this, there is a, taking a function here, expanding it at the point P, produces an element in G hat, and so it acts here. And so the way in which the classical space of coinvariants are defined is just given by the quotient, or it's the space of coinvariance. So in this case, we can define covariance. And so this is the definition that Tsuchiya, Ueno, Yamada gave. And one can see that a priori this should depend on the choice of coordinates. So this t is the coordinate at the point p, but it's possible to forget the coordinate. And Tsushimoto gives a nice description, which is coordinate free. So meaning that it really depends on C and P and not CP and the local coordinate at P, which is this T should be thought as the local coordinate at P. Is there a question? Oh, sorry, I just, no, it's G hat of this. Yeah, it's just, yeah, I sometimes put things together, although it's not really correct. Yeah, tensor products are not very good with Laurent series. Yeah, okay, so I want to sort of mimic the same thing. And so if I want to mimic the same thing, the idea is that this space, like if I start with another vertex algebra, not necessarily this one, coming from a simple Lie algebra, I would like it to be a quotient of M by maybe some Lie algebra acting by the action of a Lie algebra. And this Lie algebra should sort of encode the geometry of the curve, but also, of course, encoding the fact that M is a V modules. Right? In the same way here, if you notice, in the numerator, the module doesn't see the geometry. Like the numerator here, when I take coinvariance, there is nothing that sees the geometry here. The geometry is all in this Lie algebra. And so we want to do something similar, and this is where I'm going to, the approach of Frankel and Benz-V comes handy. And I just want to mention that this work for genus 0 was already done by Nakatomi and Tsuchiya. But I'm working with general G. So how do we construct this? Well, when the curve is smooth, Frankel and Benz-V tells me that I can construct a sheaf of, let's say, there's a sheaf version of my vertex algebra V. Essentially, to each point, I have a copy of V, but to describe really what a vertex algebra is, I should need to tell you also what the state to field correspondence, and there I should take a coordinate, and there is a way to forget the coordinate. So it's something that we have that they explain very well in their book, using the conformal structure. And furthermore, there is a connection which really lifts the action of the Virasoro, so this sort of is a coordinate reversion of L minus 1 plus d dt. Right? So there's a way of lifting it. And so we can define this Lie algebra, which now we'll define, I will call LC minus P of V, call it chiral Lie algebra. So we define it to just be, or they define it, you take this sequence and you just want to take the co-kernel and take the section on the curve minus the point. So it turns out that this naturally maps on, this is the disk around the point P minus the point itself. So I can just, if I have a section on the curve minus the point, I can further restrict it to a section on the disk minus the point. And this is isomorphic to So let's say to this Lie algebra using really the description that this connection is given by this formula locally. So this is the Lie algebra. And so maybe it's more correct to say that it's the LC minus P is the image of this space in here, and it turns out that it's actually a Lie algebra, so a Lie subalgebra of this space here. So the bracket is closed. And so we define, and this naturally acts maybe on M, of course, and so this is defined in this way, in the case when C is smooth. And here I'm putting under the rug some like coordinate-free dependence. One should maybe define a coordinate-free version of M so that this acts without choosing a coordinate. Right here, maybe let me emphasize that this isomorphism that I choose here will depend on the coordinate. So the action on M itself will depend on the coordinate. But there is a way in which I can actually make a coordinate-free version of M so that the action is coordinate independent. And I need for this M simple, because I will need to use some descent. Or I can, yeah. So what to do when C is nodal? Right, so we know what to do when C is smooth, and I said this is sort of known. And for nodal, well, with my collaborators, we sort of first thought, we have like a series of papers. And in the first paper, we gave a definition, and in the second paper, we actually realized that definition gave us some properties, but not the ones we wanted. So the way in which we define it when C is nodal, and let's assume just it's irreducible and have only one node. How do we define this space? And this is called, maybe I just say it out loud without writing, this is the space of coinvariance. And its dual, it's the space of conformal blocks. Just to set some terminology that I think I didn't write down before. Well, how do we define this space of coinvariance in the case of nodal? Well, the idea is that let's stare at this formula for a second. So here we have differentials. So we know that the correct analog of sheaf of differentials for nodal curves would be the dualizing sheaf. And we know that, so this should be the sort of analog of this. And this is described, or can be described, using appropriate differentials on the normalization. So again, and I have the 2 points here, where I can have poles at the 2 points. So maybe in another way of saying is that every time you have a nodal curve, and this is you will see it's really related to the factorization property I said before. Every time you have a nodal curve, you can think of it as being obtained from the normalization using some glue-in data. And this is true, for instance, by this sheaf. And we essentially say that we define LC minus P of V as an appropriate Lie subalgebra of the Chiral algebra, which is defined on the normalization, where not only we have to remove, the point P that was marked here, but also we need to essentially mark it by the 2 points there. And the condition that it has to satisfy is essentially similar to the ones that we have here, meaning you take your sections, so you have some essentially would be global sections on C minus those points, and when you expand those at the points Q plus and Q minus, you need to satisfy certain conditions, which are similar to the residue conditions, but will involve also the involution, I guess it's called theta of V, something that so will appear there. So there is some work to do. So we can define it, and the thing is that this definition actually can be further generalized to the case in which your curve, we have a curve which is smooth, we have a curve which is nodal, but we would really like to define this, in order to show that it's a sheaf, we would like to define our own family of curves. So it's possible to define it also for family of curves. In a similar way, essentially, using the fact that describing what a versal curve is and proceeding similarly. It's a bit more involved, but it is possible to do. And so the upshot is, let me maybe right here, is that with this correct definition, or with this definition, that I know I didn't give all the details, but I just wanted to give you the idea of how this is achieved. That this, meaning that description, defines a quasi-coherent sheaf on MG and bar, let me say, which is, well, denoted this would be MG1, but you can already imagine that essentially I can take more points. Let me just go back. I'm sorry for the camera, that has to move. But if I have more points, then in this case, we have M1 tensor Mn. And similarly here. So, and here we have minus all the points. And I will just sometimes write M bullet to mean their tensor product. So let me say, to define, so to just have this coherent, quasi-coherent sheaf, we do not need any further conditions than the ones I wrote. Yeah, like CFT type only, I guess. Yeah, and we need the modules to be simple just because we want to forget coordinates. If we don't care about coordinates, we could also just do it without simple. Yeah. So, thank you for the question. But
sorry, can I, another question?
Yeah.
So if the modules are not z-graded but sort of shifted from z-graded, do you also need a choice of tangent vector at each point?
Yeah. So this is the thing. So we are. If they are simple, then I can have, since I have a conformal way, then we don't need a tangent vector, because like if you think about, I mean, my grading is not given by the action of L0, right? So I impose the gradient to be on integers. I impose the gradient to be on integers, and then L0 acts by a shift of the degree. And then I don't need any more. A priori you would need it, but I can sort of,
okay, so
virtually, I can twist by, I descend, so I first forget everything except the tangent direction, and then we do similar to what Tsushimoto does, in the sense of we twist by something, then we can descend, and then we untwist back. Because in the case of a finely algebra, also in that case, there would not be, L0 doesn't act by integers.
Right.
Yeah.
Okay.
But this is where we use the fact that the modules are simple is to be able to forget the tangent data and to do this last step. Otherwise, we would always need the some tangency condition, because we wouldn't be able to do that step.
Yeah.
Does it answer your question?
Well, yeah.
Or we can talk more later for more details. But the idea is that maybe, let me say that for the case of a finely algebra also here, like L0 doesn't act with integral values.
Right.
But it is possible to still descend it, forgetting the tangent vector. So we do the same thing there.
Okay. Yeah.
It's, the moral is that in that case work, and we just adapt their methods.
Yeah.
I mean, Tsushimoto's method.
Okay.
Yeah.
Thanks.
You're welcome. Are there other questions?
sorry, maybe it's a dumb question, but how is this related to flat sections? This H0 of this co-kernel?
How is this related?
You know, like usually if I had a coherent sheaf and a flat connection, I might take flat sections. What you wrote there, I mean.
I have to think about it. Sorry, yeah.
Okay, thanks.
Yeah, I mean, I'm on a curve, right? So all the connections are flat. But
yeah,
really, I don't understand the question. We can talk.
This H0 of the quotient, like, it's.
We can talk later, maybe. Sorry, okay, so we have this, and we denote it in this way, and it's called the sheaf of coinvariance. But saying quasi-coherent doesn't mean much. Like, it might be infinite dimensional. It just means it's a basic property you want for a sheaf of modules. Like, it doesn't have some weird jumping here and there. And we can say something more. So we know that on MGN, it has a projectively flat connection. So this is something that Frank and Vensby already noticed. They assume the condition that we're integrally graded, but we can drop that assumption. At the boundary, you might have some problems. So and it doesn't extend to the boundary. And then let's say if V is C2 cofinite and rational, just some properties, then this vector, this sheaf, let me call it. Sometimes I will denote it in this way, is actually a locally free of finite rank. And we say n satisfies factorization. So let me maybe say a couple of words on this part, like where do we use this assumption and whether we can drop something. So maybe the first observation, and this is maybe remarks on the proof, the first observation is that we can use the C2 cofiniteness condition to prove that actually these sheaves, they are coherent on MGN bar. Oh, sorry, on MGN. Coherent just means that the spaces are finite dimensional. So on the locus of smooth curves, C2 is a sufficient condition to ensure finite dimensionality. I guess, I mean, this is not necessary. I guess the works of von Ekeren and Heluani tell us that we can assume a little bit less, for instance, in genus 1. But for higher genus, we can, C2 is enough to do this. And now, maybe something that we can say at this moment is that now we can already conclude that the sheaf is locally free on MGN. Why? Well, because if you have a sheaf which is essentially finitely generated, it's coherent, all the fibers are finite dimensional, and you have a projectively flat connection, you can show that there cannot be any relations there. So if you have a relation, you can always do some induction to maybe decrease the number generators. And so you can show that it's really locally free there. So on the open part, okay, we already are in good shape. So now, how do we extend this result to the boundary? Well, by what maybe I said earlier about factorization, factorization should be a way of telling us what happens on the boundary, knowing what happens on the interior, because it should tell us how to decompose it. So, let me just write it on the board. So we are left to, we want to extend this to the boundary using factorization and a more refined version of factorization, actually Sowin theorem. And this is where we actually use rationality. So let me state what the factorization looks like explicitly. I guess many of you already maybe have seen this, but so, and let me again, now I want to use a pictorial description of my spaces. So instead of writing V of C, P, V, and M, I just want to do this. So suppose I have a curve where maybe it's only marked by one point, and here it's associated with the representation M. Right? This means that I have a curve. So this is the notation for C, P, V, M. Okay, I would really like to write papers where I can just use these instead of notation. Would make my life a bit easier, but yeah. Anyhow, I think it's more intuitive to see what happens. So I have this space, and what I can do is that, and I can have more points, but let me just assume it's one for simplicity. I can take the normalization. Okay, so now I take the normalization. I have Q plus and Q minus, and I have again my point P. Now, in this normalization, I have 3 points. So I should give to each point a representation. Right, in the same way here, P, I had the representation M, or the module M. I'd better have the same representation here. But I have two extra points, so I should have 2 extra modules. So what I can do is that, well, let me take W here, and maybe I take the controgradient module on the other one. So this is possible. I can take this in, let's say, V module. This really means simple V modules. And I can take the covariance associated with this data, take a direct sum over this space, and factorization tells us that this is isomorphism. And so rationality tells us this is a finite sum, for instance, and actually, and to prove this result, we heavily used Joux's algebra and essentially induce the fact that all the modules are induced from modules of the Joux's algebra, which turns out to be, finite and semi-simple, and then we can use Wedderburn's theorem. So these essentially tell us that we can have this decomposition. And a key factor is the fact that our chiral algebra, which was crucial to define this object, is also defined in terms of the normalization. And so we could really be able to go back and forth between what happened on a nodal curve and what happens on its normalization. But it's not, it's not by definition that it is true. Like some people say, well, you can just define your vector space at nodal curves, imposing factorization. Say, yeah, but then how do you show that they actually vary nicely in families? You have to really go back down to define this. So maybe the conclusion I want to say now is that, before going to the last part of the talk, is that really the correct definition of the chiral algebra, we knew it was correct because we could prove factorization, essentially. And there is a more refined version, which is the Sowin theorem, which essentially doesn't only work with factorization with a curve over a point, which is nodal, but on a small deformation, so on a formal neighborhood. And it's crucial to actually extend this to the boundary. And maybe something some people always ask me a question about what happens if, a priori my curve can be something like this. I can have many components. And one of the conditions that Tsuchiya, Ueno, and Yamada impose is actually I have a point on each component, but I never mentioned this. And this is because we have propagation of vacua, which was actually proven by Codogni, and his proof essentially works also, in our case, it's just some mild extension that allow us to actually drop that assumption. This is more like a technical thing that it's really crucial, like this proof of propagation of vacua. And maybe let me mention that both factorization and propagation of vacua, for if any of you is more like into algebraic geometry, can be seen as sort of compatibility under tautological maps of these sheaves. It means I pull back of these sheaves and the tautological maps are still sort of sums of coinvariance. So I have 9 minutes, and in these 9 minutes, I want to say something more about other properties. So I want to keep this here. And the other properties at the beginning, I talked about global generation. Why did I talk about global generation? Well, because in the work of, the coinvariants, which are constructed by finely algebras, by Tsuchiya, Ueno, and Yamada, were proven to be globally generated. This is works of Fakhrudin and Ueno. Right, so maybe let me say this. If you are on genus 0 and you put any representations, let me call them M to the left, these are globally generated. Meaning they are quotient, and the reason is that essentially in this case you can describe this space as really being the quotient of, let me say, tensor products of, let me call them V lambdas, where H lambda I, where each M I was in the notation I used before. Okay? So we can find some space classically that surjects there so that this actually extends to family and this is constant. Well, in our situation, so in general for us, this is not true. And I would like to say, when I first did some computation and I saw this was false, and I will tell you in a second why, I was very sad because in the past, like my collaborator, Angela Gibney, has used this property of being globally generated to study the modular space MGN bar. Why? Well, if it's globally generated, essentially, you can produce maps to projective spaces and maybe find other models. So you can study the geometry of MGN bar. And if this is not globally generated, then you cannot use these conformal blocks to do that. Or maybe you cannot use all of them. And why? Why is this? Why does this not hold in general? Well, I didn't write that in the properties, but factorization actually implies that not only we can then compute the rank recursively, like using induction on the genus. I didn't write it down, but of course, the Berlin, the formula will then give you the ranks of this. But you can actually compute other numerical invariants, like all the Chern classes explicitly, when V is the set contragradient under that extra assumption. So in that case, we know that these Chern classes need to satisfy some positivity conditions, and if they were globally generated, but they don't. So, so we really found there are counterexamples. Using like 0, 0, for instance, or some lattices, or some lattice representation. Sorry, lattices VOA. So we really could find some examples using computation of Chern classes. And so it's natural to ask, okay, what is, like, under which assumption is globally generated, can we know? And this is the work with Angela Gibney and myself. And we said that, well, if V is generated in degree 1, and here I'm not assuming C2 or rational, then on genus 0, let's see, these shifts are globally generated. So, of course, if I impose extra condition, these would be like tensor products of the affine algebras. So it's not that you recover something that's new, but we don't really assume that assumptions. Like, you don't really need to be of the form tensor product to get this. But it seems like the crucial part is to be really that the degree 1 determines your whole module, your vertex algebra in the modules, and so essentially you reduce your proof, which is similar in flavor to what Ueno and Fakrudin gave in the past, but of course it's more involved because the Chiral algebra we use is more complicated. It's slightly more involved. So, yeah. And in the last 3 minutes, let me talk about maybe some open questions that are left, so that I'm interested in exploring. So, so one question is, well, how do we, let's remove rationality, right? So that's the first thing one can think. So, and I'm curious to see if the talk next to mine will help me understand in this situation. Like this, so this is I'm working on this together with Angela Gibney and Danny Krashen, and the idea, it seems that essentially you might have a form of factorization which is a bit less explicit than the one I gave, essentially because your Jou algebra is not as beautiful as you would like, and you cannot just use Wedderburn's theorem, directly. You need to take some resolution. So it seems that you can still have a factorization, but which it becomes a bit more opaque. And so this is something that we are working on. And so I look forward to talk with many of you this week on this, because I'm not an expert on vertex algebras, and so I sometimes these conditions seems very hard for me to work. So I have until Friday to solve this problem here. Okay, I'm on a mission. Okay, and the second question, which actually is something that it's maybe going back to the Lie algebra case, is whether we can have a modular interpretation. What do I mean by this? I know this can be a very misleading word. It means that, so classically, so if I take this, and I take itself, meaning I take itself as a representation, take the trivial representation, maybe before I denoted C, and I take the conformal blocks, we know that this is isomorphic to, oh, and here there's a curve and a point. It's isomorphic to a space of global sections of generalized theta function on appropriate moduli space, where G is a simple group whose Lie algebra is small g. And the question is, if you start with some vertex algebra, which can be as nice as you want, but it's not really an affine Lie algebra, there's not a direct relation with a Lie algebra, an affine Lie algebra, is it still possible to give a description of conformal blocks in this sense? And there are different approaches one can follow, and if you're interested in this, I can talk with you more during the breaks or in the next days. But I mean, to me, this is like, maybe this is where I started, when I started doing math seriously. It's where I was interested in Bun-G, and so this is why I started thinking about conformal blocks. And now I would like to go back and think, okay, can we still go back there for some G, or just some question? Maybe the correct question is, can I describe V on CP, V, let's take V itself. Is this the same of a Chiral of something, where I don't know what those somethings are? And thank you, sorry, I'm a bit over time.
Is there any questions in Zoom or in the room? Maybe.
May I have a question?
Where? Sorry. Who?
In June.
Ah, okay.
Is it available that marked point P is to be double point in nodal curve?
Sorry, can you repeat?
Marked point P is to be double point in nodal curve?
It's always a simple point. It's always a smooth point, the points where I put them, yeah.
Okay, thank you.
You're welcome. I mean, one can interpret factorization as thinking that you actually put the trivial module at the node, and you would like to say what happens there. But, yeah. But all my points, yeah, so all my points here are always nodes. Thank you.
Okay. Any other questions or comments?
Thanks. So in the case your category is not semi-simple, what factorization look like?
When it's not semi-simple?
Yes.
This is work in progress. Yeah, I mean,
okay, but
it's
more or less.
Okay, so what I can say is the following. Let me erase something. Okay, so what we have is, let's just have, you have only 1 point. Suppose you start with 1 point. And what you have is that you can take, well, A of V is the Chiral algebra, and let me call maybe Z the following thing. So I take the enveloping algebra of V. So I induce a V module from A of V. And then I can always send M to itself. And is just the 1 there. So this is possible. And if I quotient out by an appropriate chiral algebra, so here I'm on the normalization actually. It turns out that, let me see, yeah, so there is a modified version of your chiral algebra which has some weights at the point Q plus and Q minus. So it induces an isomorphism here, and here you don't need rationality. Then what you can say is that then your usual conformal coinvariants are a further quotient of this. So you can further quotient out by an appropriate, I can put an appropriate subset here, or ideal. And when you quotient out there, here you really have, let me call it Z tensor Z bar. Something. And here what you obtain is really V at the norm, at the smooth curve, at the nodal curve. This is normalization. Sorry, there is just a lot of annotation that I need to. So you quotient out by something, and it turns out that these two things are isomorphous. isomorphic. But then the quotient that you choose is such that when this is semi-simple, this decomposes as sums of V and its contragradient. And so when it's not, you just have an uglier description. And so the point is that you want to just describe this Z tensor Z bar as a co-kernel of essentially a resolution here. I don't know if this answers your question, but it's a matter of the proof that we had. There are some steps where rationality doesn't appear really, or maybe we use it but we didn't have to use, so we are checking all the things, or where do we actually use, once you assume C2 and rational, to me it felt like everything was perfect, and then I said I didn't really remember which condition implied what, and so it's a matter of tracing back all the assumptions where we use it. But for sure, rationality tells you that this is super beautiful using Wedderburn's theorem, which you wouldn't have in principle, but you would still have this condition, and then it's a matter of finding the correct resolutions. Yeah.
Okay, thanks. So if there is no any more question, one more question. Okay.
Is there some expectation of analogous results for higher degree chiral homology?
I am not an expert on that field, but yeah, sorry, I don't know anything about higher dimensional. Yeah, and because I guess it's trivial when it's not rational, or it's considered trivial when it's rational. So, so that's the problem.
One other thing about the projective flatness. So you have that result on MGN, but not the compactification. Is it possible to try to extend, to say something like a twisted D module on MGN bar?
Yes. So I wrote here DGT1, 2, and 3. It's a series of papers. In DGT1, we define what the generalization was on MGN bar, where they were twisted. They had a twisted D module structure, but it was not with that chiral algebra. It was with another one. So it's interesting. It seems like you win in one place, you lose the other way. Maybe they are the same, but it's really not clear. So it is possible to do it in a way, but it's not. And these things coincide on MGN, but they sort of extend. There's not a unique extension. So.
That was the one that you said is maybe not obviously correct or something.
Right. Yeah. So it depends what you want to do. If you care more about twisted D modules, then you might want to do the other things. But then you have no idea whether they are finite dimension. Just good luck with everything else. But yeah.
Thank you.
Thank you.
Okay, no more questions. So we thanks again the speaker. And since